So if we want to determine if a function is one-to-one, right, and why we would want to do this is that a one-to-one function has an inverse function, right? It is invertible. If we want to determine if a function is one-to-one, it can actually be kind of tricky, and there's a few different ways that we could approach it. We could approach it by looking at the graph of the function using the horizontal line test, or we could try a more algebraic approach. So the graphing method will, of course, be more helpful if you're familiar with the graph of the function, or if you are familiar with the general properties associated with that kind of graph, like if it's a common type of graph, right? Like our trusty f of x equals x squared, we should be very familiar with at this point, right? We don't need to draw it exactly. We're just trying to look on if it would pass the horizontal line test or not. And we can clearly see that this will not, right? Any horizontal line drawn anywhere on the graph except for at 0 would cross two different points. And this is because, if we did f of 2, we're going to get 4. If we did f of negative 2, we're also going to get 4. Right, so we get the two x values are mapped to the same y value. So this function does not have an inverse, even though if we think about x squared, it has a pretty natural inverse, which would be the square root of x. So how do we kind of rectify those two things? Well, when we actually look at finding inverses, what we'll see is that maybe if we restrict the domain, like maybe if we only look at the right half of this graph, then we could define the inverse, which would be the square root of x. And that makes sense in that context because we can't take the square root of negative numbers anyway, right? So considering the negative numbers doesn't really, do anything for us in that context anyway. So we'll be able to do things like that. But just focusing now on if a function is one-to-one, here we say no. This function is not one-to-one. So it's not invertible, and what we mean by that is that if we are considering the entire domain, it's not invertible. So sometimes we can restrict the domain and just look at parts of it and see if it's invertible there. Some other graphs, maybe we look at f of x equals x cubed. Okay. So again, just doing quick sketches of these graphs based on the parent graphs that we looked at. This one, everything looks perfectly fine, right? It's not going to fail that horizontal line test anywhere, right? If we draw a horizontal line anywhere here, it's only going to pass through one point. So it looks like, yes, this is going to be invertible. Okay. Maybe it's quicker if we just look exactly at the parent graphs that we went over in a previous video here, and just go through, okay, is this invertible? Is it not invertible? Right, so straight line, it is invertible, right? Horizontal line test, that's all we're thinking about. It's going to pass the horizontal line test. Constant function, not invertible, right? It's going to fail the horizontal line test right here. And actually in this case, it's because if we did find the inverse, it would be a vertical line, which is not a function, right? A vertical line can't be a function. And that's kind of the idea here, is that if it doesn't have an inverse, if we were to invert it anyway, we would get something that's not a function, right? Absolute value function, not invertible, does not pass the horizontal line test. X squared we just looked at, x cubed we just looked at. Rational function is invertible. It's actually its own inverse is what we're going to see. The inverse function of 1 over x is 1 over x. So that's kind of an interesting case. Square root function is invertible. It's going to be kind of a weird case. Its inverse is going to be half of the x squared function, actually. The cube root function is invertible. This should be the inverse of the x cubed function, right? Naturally, those should be inverses of each other if our definitions make sense, and that was all that we did. So just thinking about some other common graphs we'll see later that we did not define on the parent graph section. There's some graphs known as exponential graphs. Okay, they look like this. And we can see that this one is invertible. So just looking at the horizontal line test, there are ones called logarithmic graphs, which are actually the inverses of the exponential graphs. We can see that these are invertible. So just previewing some common graphs that we'll see later. When we look at the trigonometric graphs, those we'll actually see are not invertible because they look like this, right? They look like waves. So these are not invertible, which might be a little bit surprising if you look at any standard calculator. If you look at the trig function, sine, cosine, and tangent, you'll see on there inverse sine, inverse cosine, inverse tangent. So clearly there's a way to define these functions, and again, it's going to be by just restricting the domain. Depending on the function, you'll just restrict the domain to just one little part of it, and you'll define the inverse function on that part. So we can kind of play around with it in this way, but just thinking about if these functions are one-to-one, we're considering the entire domain. Okay, so now algebraically, so to do this, we really need to think about the technical definition of what it means for something to be one-to-one, which is that a function is one-to-one if f of x equals f of y implies x equals y. Okay. You see this definition a lot more like when you're doing proof-based things, like proving things in classes, because this is the more technical definition, but this can be helpful to think about if the function's one-to-one algebraically. Normally, we're just going to look at functions where we're familiar with the graph, but this can be helpful for a more general case. So f of x equals f of y implies that x equals y. What this tells us is that if two outputs are the same, they must be coming from the same input. In other words, if we had something like f of 2 equals f of 3, okay, or actually, maybe we'll use one where we've already seen where this is true, right? F of 2 equals f of negative 2 on f of x equals x squared. Right, we saw that this is true. F of 2 does equal f of negative 2, but clearly 2 does not equal negative 2. So this is how we know this is not one-to-one, because it doesn't satisfy this condition. So something where it would satisfy this condition, if we think about the simplest case, maybe f of x equals x, right? Just the straight line. Then if we think about f of x equals f of y, well, if we replace these with their corresponding parts, right? F of x is equal to x. F of y is equal to y. So we do get that x is equal to y. Okay. Maybe it's clearer to see it if I write it this way. Okay. So this one's a very simple case. There's nothing really to do here. All right, so we ultimately get the equality here that x is equal to y. If we were looking at maybe the x cubed case, f of x equals x cubed. So we start with f of x equals f of y, which is x cubed equals y cubed. And then we take the cube root of both sides. Okay, so we're using equation solving techniques here. And when we do that, we get unique answers x equals y. And this tells us that it is 1-to-1. Okay. So this might kind of seem simple in this case, like why can't you just do this for any function? If we algebraically tried this with the x squared function, for example, f of x equals f of y, x squared equals y squared, when we take the square root of both sides, we don't just get one answer. We get x equals plus or minus y. And we'll talk about this more in depth when we look at these quadratic equations, but we kind of already saw an example of this with 2 and -2. Both of those numbers squared give you the same value. So when you are considering these equations and you're taking the square root, you have to think of both the positive and negative parts of that. So f of x equals f of y doesn't imply that x equals y in this case, because x could be negative y. So we're looking for things like that, where we might not get a unique answer on both sides. Okay. Just one more, I guess. Let's look at 1 over x, because that's one we haven't looked at how to graph at all. So maybe this algebraic method might help us. We did see the graph of it, but we haven't really looked at the functions in depth or anything. Okay. So this is going to be 1 over x equals 1 over y. And to solve this, well, we'd have to multiply both sides by y. So we get y over x equals 1, and then multiply both sides by x. So we get y equals x. In other words, x equals y. Okay, so we do get a unique answer here. So there's no operation that is introducing multiple answers. That's what would cause us issues. So this is a more concrete, proofy way of showing that functions are 1-to-1 and therefore have inverses. But like I said, in most of the cases that we're going to look at, we can default to the graph, because they will be functions that we will at least have looked at the parent graph for.